Okay, so in this lecture I would like to talk about a different version control system than the one that I've talked to you about before, namely Git. So Git is a program that originated with the same people who wrote the Linux kernel. And what they wanted is a system that is more flexible than Subversion. In particular, what they like, or what they wanted to have, is a system that allows you to have multiple repositories that somehow communicate with each other. So in Subversion, there is really only one central location, and if you wanted to do something, if you wanted to implement something, you would create a branch, for example, like I explained to you in the previous lecture, and then you could do on your branch whatever you want, because it doesn't affect what everybody else does, and at the end you could merge it back. But it turns out that this is a little bit of an inflexible arrangement, because when you do this, then the only people who can branch and commit to the repository are the ones who have write access. And that means that you have to keep track of, let's say, who is able to commit to something. You can't just say to somebody, okay, well, yeah, you wanted to implement something, right? Why don't you just commit things into our central repository? That's not how SVN works. So if you have somebody who is, let's say, an infrequent contributor, or somebody who's new to a project, they did not usually have the benefits of a version control system, because they just didn't get write access to the repository. And as a consequence, they oftentimes, well, maybe they developed on their own hard drive and had to do local backups or something, but they could not commit individual steps that at the end you could merge back. So Git was invented as a way around this, and it has, I think it's about 10 years old by now. It has grown in many different directions, but is really, if you think about it, and if you start using it, an ingenious system that helps multiple people to work together, because everybody has their own repository. And then what happens is that you move patches from one repository to another repository. Let's say from the central one to yours, you keep developing, you can commit to it because it's your own repository. And at the very end of it, instead of doing a merge, essentially you say, well, here's the sort of patches that I would like you to consider. And then the big manager of the project says, yeah, that looks good. And he takes the patches from your repository, where he only has read access, and he moves it into the central repository where he does have write access. So that's sort of the way we get around this problem of write access to a repository. Everybody has only write access to their own repository. But if you have read access to another repository, you can get branches, or you can get patches that merge from one repository into another one, or move from one to another one. So let me give you a little bit of the, let's say, philosophical overview of what Git does, and then I'm going to show you a few examples of the sort of things that you can do with Git. Git is a powerful but also complicated system. And I'm not going to even try to be comprehensive. It's also very hard to do this on just a single computer where you don't have internet access like we do have here in the studio. So many of the things that you can do with Git, I'm not going to be able to demonstrate, but one of the nice things that comes out of this development of Git is that there is an incredible number of tutorials online that you can use. So if you Google for Git create clone of repository, you will find 12 different repositories that all talk about how to do this. So there's many resources that you can use. So let's take a look at a few of the things that Git can do. So this is lecture 32.75. Git has a different repository than Subversion, like I told you. There is a, let's say, every project has something like an official repository, okay? But then there are many other repositories that belong to individual people. So in my particular case, let's say I want to develop something, then I would have a local copy of the whole repository, okay? Now the terminology for this is called a clone, okay? So a clone is also a repository. And it is in the original case, let's say a copy of the then current state of the central repository. But of course, as people commit things or merge things into the central repository, my clone may be outdated, but it may also, in addition to what's in the central repository, have changes that I have made. So the two of them can diverge. And one of the things that you have to do when you want to do serious development is that you periodically take the changes that have happened in the central repository and merge them into your local copy, into the clone. Okay. So these are clones. I can check out a working copy from my own clone. I could also check out a working copy from the central repository, of course, but in general, I cannot commit into the central repository. So by and large, we only check out from and into the local clone. Then further towards terminology, so when I move changes from the central repository, which we often call upstream, then that process is called pull. So that means if people have committed things into the central repository, I want to get it into my local clone, then that operation is called a pull. And if I want to move changes from my local clone into the central repository, then that would be called a push. And I should say that central repository is sort of it's a sociological construct. We all agree that, let's say, one particular repository is the central one, but in reality, that could be also the repository of some other contributor. So let's say there's the deal.II repository, there's my own repository. I'm working with one of my students who has a clone of my repository. He keeps pulling changes that I have made to my repository, makes local changes, then pushes it, and it goes into mine. And let's say I can continue to push it back into the central repository. So what is upstream and what is central depends on your point of view. There are many repositories that, let's say, logically, all, or let's say, physically, are all independent of each other. And which is central is just something what a group of people agree upon. Okay, so this is how you have to think about this in Git. Okay, so to continue here, this concept really has many different advantages. So one of the things is that I can consider my own repository, my clone, as a branch of the central repository. Typically, so you can have clones that are online on some website, but you can also have a clone that actually sits on your local hard drive. And that has the advantage that you can work offline. Now, of course, I record this in 2015, where it doesn't happen that often anymore that we actually are offline. But if you're sitting at the airport or in a train or on the plane, you can continue to commit into your local clone. And then when you get back to a place where you do have connectivity, you can push the changes that you made into your local hard drive clone. You can push them into an online repository, for example. This approach of multiple repositories has another advantage that, let's say, if you do development with others, you can pull patches from the central repository, but you can also pull changes that somebody else has made in their own clone. So let's say we both want to implement something that's not ready for the central repository yet. We can pull patches from each other's repository into our own clones. In Git, it turns out that that branches are somehow more natural. We do it all the time, that we create branches in Git, which is something that in Subversion I think people are rather reluctant to do for reasons that I think have less to do with technical restrictions than just with, let's say, the way we operate this program. So oftentimes the question of how we interact with a program is not so much determined by the technical details of this program, but let's say how, as a community, we use it. And I think in Git, let's say as a community, if you asked others how they do it, you learn from them. The user community has just converged to using branches much more liberally than we have done in SVN. And I think a lot of it has to do that, let's say it's a little bit easier to do. It happens on my own hard drive, so creating branches as a throwaway branch just to try out something is very natural because it happens on my own hard drive. nobody's ever going to see it. Whereas in Subversion, if I do this in the central repository, then it's there. And because I never touch the history of a central repository, if you do some development on a branch that goes nowhere, it will always be visible in SVN. It's always there. So I think it's more, let's say, a sociological construct that we use it this way, but I think these are good reasons to do it that way. Further, so for reasons that I have not completely understood, Git actually seems to work better with inexperienced developers, and I think maybe that comes down to the same issues, that as an inexperienced developer, you're probably reluctant to commit into a public repository that everybody can see, whereas it's totally fine if you commit into your own repository, which is sitting on your hard drive, and nobody will ever see if you make a mistake. Of course, I tell my students that, well, you making a mistake is a teaching opportunity for me, right? So you shouldn't be afraid of making mistakes. You shouldn't be afraid of sometimes breaking stuff. This is just how software development goes. But I understand the reluctance to do this. And so Git is something that I think makes this a lot easier. The downside of Git is it's a more difficult model, and that's one of the reasons why I wanted to show you how SVN works before, because it sets the stage for many of the concepts that we use in Git. Like I said, there are many online tutorials that can help you there. So before I go to show you a few examples, in Git, I want to talk about terminology a little bit. So in Subversion, we said mainline is a branch that exists that by convention is stored in the trunk subdirectory of the repository, and that we consider as, let's say, the main development line from which we can develop, let's say, releases, for example. And everything that is not ready for production time by default should not be in mainline. The same concept, of course, exists in Git, and it is called master. So master, again, is just a name. It is a construct we agree by convention that master is the main development line. In Git, because you have many repositories, there is the concept of an origin. So if I have a local copy of a repository that I call B on my own hard drive, then by convention we're going to say that origin is the place where I copied that repository from which I cloned it. Okay, so if I cloned A into my local copy B, then A is the origin of B. And if A itself was cloned from somewhere else, then I will call that repository upstream. So you can think of A as being the let's say, parent of B, and upstream being the grandparent of B. These are, again, things that can be changed. So what I consider as upstream, for example, might for somebody else be just another repository. These are just, let's say, terms that allow us to flow patches from one repository to another one. Other things. So in Subversion, you typically think of, let's say, a revision as something that denotes the state of the code after n revisions have been made. So when somebody says in version 5, for example, then what they mean is the collection of source files at the time when revision 5 was committed. So that's something like the state. Okay. Every commit results in a new version and a new state of the repository. In Git, we don't actually like to think about the state. In Git, what it really is just a collection of patches. So after a commit, you just get another patch that goes, for example, into the master branch. But there is no collective state, so it's not like we would often think of it. I mean, in practice, there is a state, of course. After a commit, I can look at the entire set of files that I have, and I can say, this is how they look like. So there is a state, but we don't think of a Git repository as something that has state. It is just a collection of patches, and if I add a commit, then that collection of patches just has one more patch to it. And we do this because in Git sometimes you want to reorder patches. Okay, so let's say you would like to, you have revisions, let's say 3, 4, and 5, and then one of the things that you could do is you could reorder patches 5 and 4. Sometimes you want to do this, maybe not that important right now to explain why, but that's sort of the way we think of it, that it's a collection of patches, one on top of the other, but they can be changed, and so there's no global state that is fundamentally associated with this. Okay, one of the things that you have to understand in Git is that there are no revision numbers. So in Subversion, there is only one repository, and whenever you commit into it, you turn up the revision number by 1. And as a matter of fact, it doesn't matter whether you commit to mainline or to a branch, the revision number will be incremented by 1. That works because there is only one repository, and so a revision number is unique, right? It tells you exactly what the state is. In Git, there are many repositories, and so you can't say, you know, please check out revision 5, and you will see that if you use this particular input file, then the output is wrong. That does not work because you may have made more changes to your local repository, somebody else may have made more changes to the central repository, and as a consequence, the revision numbers in your clone of the repository do not match anymore the ones of the central repository. So, because there is no repository that is, let's say, syntactically superior to the others, there is no place to designate official revision numbers, right? I mean, in order for there to be unique revision numbers, every repository would have to ask, let's say, the upstream what the next number would be, and if the upstream is again downstream from somebody else, you would have to have this chain. But that requires you to have one central repository that really is able to determine what the next number would be, and that's not how Git works. In Git, all of the repositories are logically equal. So there's no place where you can ask what the next revision number would be, and as a consequence, there can be no revision numbers that we sequentially use, because we could not agree what revision number 10 would be. Revision number 10 in your repository might be very different from revision 10 in my repository. So we need to come up with a different way of doing this. And in Git, that means that instead of revision numbers, we actually identify revisions, or actually maybe patches is the better term. So we don't identify revisions, but we identify patches by hashes. So a hash, I'm going to show this to you in a second. Maybe I'll show it to you now, and then I'll go back. So a hash is essentially a hexadecimal number. So I had that somewhere here. So this is how a hash looks like. So a patch would be identified by a number like this, a 40-digit number. Okay, I'll come back to that. So to show you a little bit about this workflow, so let's say, for example, that there is a repository to which we agree that it is central, but that's up to us, let's say, as a group to decide which we consider the central repository. Let's say it's located at deal.II.org. So let's say somebody has made 3 changes, somebody has created a branch, 3 more changes on the master. You can't read this, but this should say master here. So this is our main development source. Okay. Then let's say this person is ready here, has decided that it's time to merge this. So these merges were all merged in here. So essentially, this commit here takes all of the changes that were made from here to here to here, applies these changes on top of this one here, and then commits it as this revision. Okay. So now I come along and I say, okay, so I want to do some development too. So what I'm going to do is I'm going to clone the repository, okay, to my local hard drive or to another repository online. So there is now a repository at deal.II.org, and there's one that is my own clone, and I'm going to check out a copy. So I'm going to create a working copy. That's a directory on my hard drive where I can actually work. Okay. I'm going to continue work. In the meantime, somebody else has committed something else into the main repository. Okay. So you see that this repository is now out of date to this one here. Okay. Now, I do some work. I commit 2 more changes over here. Okay, so what you can see is that there are numbers in this graph here for illustrative purposes. So this was revision 8 here, and of course it matches exactly this revision 8. But the revision 9 that somebody else committed here has nothing to do with the development that I have made here with revision 9. Okay, so we can't agree anymore what revision 9 actually is about, which explains why we can't use numbers. Okay, so let's say these two disagree. Okay, we need to come up with a new way of numbering. These are these hashes. Okay, so instead of numbering things, we identify each patch with a hash. It's a 40-digit hexadecimal number. Most of the time, we actually only use the first 7. I don't really know why 7, probably because it's unique enough. But so we don't typically want to write out all 40 characters of this here. So a hash is computed from the ancestor of a patch. So this 40-digit number takes into account that, let's say, this commit here derived from this one, and it also takes into account what was changed. Okay. So in practice, hashes can conflict. You could conceive of 2 people creating different commits that change different parts of a file, maybe have a different ancestor, but that produce the same 40-character hash, right? So a hash is just, you know, take your 5 kilobytes of a patch and reduce it into 40 characters somehow. So in principle, it is possible that different patches create the same hash. In practice, that never happens. So people have made this argument that everybody in the world committed 1 million patches per day. It would take hundreds or thousands of years for a conflict to ever happen. So 40 characters seems to be enough to be unique. Okay, so now what we would like to do is, let's say somebody has committed this patch here. I have committed locally these 2 patches. I would like to push these patches to the main development line. Okay, so that's a 2-step process. The first thing is it creates a branch, okay, and copies my 2 patches onto this branch. And the branch, of course, is rooted in the ancestor, this one here, that also existed in this repository. Okay, so it creates a branch, copies these 2 patches there, and then it will merge this back in here. So it will take the difference between this one and this commit here and apply all of these changes on top of this one and commit it. That, of course, assumes that there is no conflict. I showed you how conflicts can happen when we talked about subversion. Let's assume that no conflict happens here. Then this is the sort of workflow that we have here. Okay, so at this point, my patches here have been brought into here. And then what I could do, for example, is I'm going to pull the one missing patch. I'm going to apply this, for example, on top here. Or let's say I'm going to create a branch and merge that back into here. But you see that, let's say, the ancestor relationship over here, so this is a direct ancestor, this is a merge here. Here, in this case, this patch here would have this as ancestor and merge these 2, whereas if I pulled this patch over here, then the patch that comes out of it has this one here as ancestor and merged in another from the side. So you see how the 2 repositories would be different, even though the current state is exactly the same. And that's sort of why we think about this Git repository not in terms of a state, but just as a collection of patches that all on top of each other lead to the current state. So I'm going to show you a few of these things in practice in a few minutes. So I have created a directory Git example. I've also created a Git repository. And because I keep forgetting how to do this, I'm just going to go back and I'm going to clone the repository into my current directory. So again, typically this here would be a web address, an HTTP something. So I'm going to, I have a repository at this location, and when I say a git clone into the current directory, I'm creating a different repository that is a clone of the original one. Okay. So in this particular case, when I say git clone here, what Git automatically does is it doesn't just clone the repository; it also creates a working directory. So I have a copy of my first program.cc in here. Okay, and now let me do some development. Okay, so I'm going to let's say, I don't know, add another variable here, I equals 64. Okay, I save this. So then I can say git status. Git status says that there is one modified file in my directory. Okay, there is also a backup file that it doesn't know anything about. Let me get rid of this just for cleanliness sake. So it says there is one modified file, and let me try to commit this. So when I say just git commit -m more modifications, of course in practice you would want to choose something that is more descriptive, then actually it says I don't know what you want to do. So git by default, if you say git commit for the current directory, it will not do anything unless you have specifically told it what you want to commit. Okay, so I have two options. Either I tell it commit this particular file by explicitly listing it on the command line. Okay, I can do this. Or if I'll show you the other way as well. So let's say I'm adding another variable j here. Okay, again git status. So I could say git add first program. Okay, so it has this here in the section changes not staged for commit. Okay, I say add. Then it's going to say this file here is changes to be committed. Okay, so now it moved into the staged for commit section. So if I say git commit with no file, now it's going to actually commit this. Okay, so I can look at the history now. So git log will show me that there are 4 revisions. Okay, they are identified by these hashes, and so I created one last night that said, you know, import a first version. We just committed declarations, then more modifications, and then I should have chosen a different commit message. These are different commits for which I just happened to choose the same commit message. Git has a very useful tool that is called git-k that can show me the history of the repository. So what you see here is the first version, for example. So it shows me the revision tree here as a, in this case, the tree is just a single line. And unlike the slides that I had before, it actually shows the oldest one at the bottom and the newest one at the top. Well, that's just what it is. So for each one of these revisions, I can now look at what changes were made. So if I look at this, so you see that, let's say if I click on this one here, remove declaration of y, that's something that I did yesterday as well. So you see here who wrote it, what's the parent, so that's the ancestor of this commit. Which branches does it live on? This was the text, the commit message. This is the change that I made. So I removed the variable declaration. This is the file that was modified. So I can click on this text here, which adds another variable I. I can click on this commit, which adds another variable j. Okay. So git-k is a useful tool to see the history. Now, What you see here is that the origin, so it's listed under remote's origin master. So this is the last state that I have pulled from the origin repository, from the repository from which I cloned my local copy. Okay, so this is where that remote repository was when I cloned it, and then I have added on top of this 2 more patches. So these things in boxes here, we call them branches. So there is a branch that corresponds to what the repository, the origin repository was. This is my current master branch. Okay, so let's say I have tested my changes and I want to bring them back into the master. So then what I would do in this case, I would say git push origin master. So that takes my own master branch and pushes it into the origin master branch. Okay, so it modifies a remote repository. And of course, it requires me to have write access to this remote repository. And let's assume that I have this, the case here. Okay, so now it has changed the remote repository. Okay. If I go here and I click F5 for refresh, then what you will see is that the remote repository has now moved. Okay, so in this case, the remote repository was brought up to the same state as where I am. If somebody had committed other things into the remote repository, then where this thing would be is not quite so clear. Okay, but what I could do in that case, I can say git pull origin master. So I'm getting all of the changes that have happened in the remote repository into my local clone. Okay, so I'm saying, well, git pull origin master. It turns out that in this case nobody has committed anything. Well, obviously not. It's also on my local hard drive. But let's say in reality, what would happen is if other people have committed something, this would download all sorts of stuff that was committed to the origin repository and would merge them into my own local repository. So that's sort of the way you interact with Git and the multiple repositories that it has. And so I think it's really useful to get familiar with Git-K, because Git-K shows you the whole history and you can look at individual patches, you can see what was changed and so on and so forth. It's a really, really useful tool. So I think I'll basically leave it at this for now. I want to discuss one additional concept that's very different between Git and Subversion. So in Subversion, like I told you in the last lecture when we talked about undoing things, in Subversion you never ever change a repository. Because if you removed a revision from a Subversion repository that's somewhere up online, then all of the people who had previously updated to that revision suddenly have a working copy that is no longer in sync with the central repository, right? So in Subversion, if you want to undo things, you only ever, you get the changes, you merge it into your current working copy, you commit it into the central repository. So you have 2 patches, one that made a mistake and one that undoes it. And that's because there is only one location and everybody has access to it. In Git, this is different. So in Git, you do this all the time, that you change the repository. As long as you do it on your local clone, that's sort of the key part. Whatever you do on your own local hard drive, nobody cares about, because you're the only one who has read access to it, right? It becomes only critical when you push something into a public repository. Those you can never touch. But as long as you do things on your local hard drive here, you can change all sorts of things. So you can delete patches that turned out to be wrong. You can combine patches. You can reorder patches if you want. All of these sort of things are pretty easy to do. And so maybe I'll even show this to you in a second. But let's say the point really is, as long as it happens in your local clone, you can do whatever you want. It may not be a particularly good idea to do this. It's good if you keep the history of a project, but you can do all sorts of things as long as you don't push them into, or as long as you don't modify a repository that's public. So I'll show this to you really quickly here. So in my local, well, no, I can't, well, okay, so let me say I add another variable ijkl, for example. I set it to 16, okay. I'm going to commit this, let's say, add variable l, okay. Now I need to say which file I want it to be, first program.cc. Okay, so I hit F5 in git k. So you see that I made this modification here. This was the addition of the variable l. Let me assume for a moment that that was a bad idea, okay? And I would just like to undo it. Well, it's on my local hard drive. I can do this. So I click on the previous version, okay? I do a right click here, and it has the option for me to reset a branch to here. So essentially, a reset means when master used to point up here, I want master instead to point up here, okay? So I'm going to say, in this case, I'm going to do a hard reset, which means everything that came after this will be lost. I want to completely get rid of it, okay? So I'm going to say OK. And so what you see is there is my master now, and it is back to the original revision, right? So the commit still exists. It still has an ancestor, but my master branch now is back to where it was. And so if I make more modifications, so write first program.cc, so you see that the variable l has disappeared. Maybe what I really wanted to do is insert a variable m. Okay, so save, add variable m instead. Okay, so I'm going to say F5 again to reload. So what you see is that that commit really still exists. It has an ancestor to where it was before, but my master branch is now up here, and it has the variable m. So I modified the history, right? I kicked a patch out of the master branch, namely this one here, and I committed another one in its stead. And these things are all fine as long as they happen in my own repository, okay? Once I push the changes that I made from my local repository to a public one, that's where it becomes critical. And the public ones, these are the ones that you can't change anymore, because other people might pull from that and might get a state that then is no longer consistent. So that's sort of the two fundamentally different concepts in Git and in SVN, that in SVN we have revision numbers, and there's only one repository that is absolutely untouchable, whereas in Git we have these hashes. Patches move around all the time between clones of repositories, and whatever you do on your local repository is your business. It only becomes public when you push a patch to some public repository. So I hope that gave you a little bit of an idea of how Git works. And Git is a complicated system. You will have to practice it. You will have to train with it. But it's a really powerful thing. It's also a lot of fun to play with for people like me. So get used to it. It's widely used these days. It's one of the two big systems that are still out there. Subversion and Git are really the only survivors of the many different systems that used to be there maybe 5 or 8 or 10 years ago. Okay.